Tonight, we drift into the darkest and most mysterious places in the universe. They are places where space folds in on itself, where time moves in strange ways, and where light, the fastest thing we know, can be trapped forever. These are the black holes, and tonight we are going to follow them from birth to death. Before we begin, take a moment to get comfortable. Let your breathing slow. The lights can fade. And as the room grows quiet, let the words carry you far away. This is a journey that begins with fire and ends in silence. Our story begins not in darkness, but in light. Long before a black hole exists, there is a star. Stars are not eternal. They are born, they live, and they die. And for a black hole to form, the star must be massive, more massive than our sun. Picture a cloud of gas in deep space. It is cold and it drifts for millions of years. But deep inside, gravity is at work. Every atom in the cloud pulls on every other atom, and slowly, the whole cloud begins to collapse inward. As it collapses, the gas in the center becomes hotter and denser, until a point is reached where hydrogen atoms begin to fuse. This is the birth of a star. For millions or even billions of years, the star shines. It burns its hydrogen into helium, releasing energy that pushes back against gravity. The star is in balance. Gravity pulling in, energy pushing out. This is the long, steady life of a star. But nothing lasts forever. Eventually, the star begins to run out of hydrogen. It starts fusing helium into heavier elements, then those elements into heavier ones still. Each new stage burns faster than the last. The core grows hotter and denser. The outer layers swell. The star becomes a giant. For a star much larger than our sun, this path ends in a spectacular way: a supernova. When the star can no longer produce energy to counter gravity, its core collapses in a fraction of a second. The outer layers are thrown into space in a massive explosion that can outshine an entire galaxy for days or weeks. What is left behind depends on the size of the star's core. If the core is small, it may become a neutron star, an object so dense that a spoonful would weigh billions of tons. But if the core is massive enough, there is no known force that can stop its collapse. Gravity wins. The core collapses into a point so small, so dense, that the laws of physics as we know them can no longer describe it. This is the birth of a black hole. At the heart of the black hole is the singularity, a point where density is infinite, where space and time as we understand them break down. Around the singularity is the event horizon, the boundary beyond which nothing can escape. Cross the event horizon and you are gone from the universe we know. The black hole does not simply sit there though, it can grow. Anything that falls into it, gas, dust, stars, even light, adds to its mass. From a distance, a black hole can only be seen by its effects on the space around it. Matter falling toward it forms an accretion disk, a swirling, glowing ring of material heated to incredible temperatures. These disks can shine brighter than an entire galaxy. Yet, no matter how bright the material around it, the black hole itself remains perfectly dark. There is a strange elegance in how a black hole shapes the universe around it. Its gravity bends light, distorting the view of the background stars. If you could get close enough, you might see the universe wrapped into a strange, circular window around the black hole, with the event horizon at its center. But getting close is a dangerous thought. The gravity near a black hole changes so sharply that the difference between your feet and your head would stretch you like a piece of string. Astronomers call this spaghettification, the pulling apart of matter by tidal forces so intense that no object can survive. Still, black holes are not just destroyers. They are also creators. The explosion that forms them scatters heavy elements across space, elements that will one day form planets, oceans, and life. The black hole itself can shape galaxies, influencing how stars form and where they gather. Some black holes are small, just a few times the mass of our Sun. Others are giants with millions or billions of times the Sun's mass. These supermassive black holes sit at the centers of galaxies, including our own Milky Way. How these giants form is still a mystery. They may begin as smaller black holes that grow over billions of years, swallowing matter and merging with others. Or they may form directly from massive clouds of gas collapsing in the early universe. Whatever their origin, they are among the most powerful objects we know. When matter falls into a supermassive black hole, it can release more energy than all the stars in the galaxy combined. And yet, for all their power, black holes are not eternal. They have a lifespan. Over unimaginable timescales, they will fade away. That part of the story comes much later. For now, imagine the moment of birth. A star has died in fire, and from its ashes, something stranger and more extreme has taken its place. The light from the supernova fades, and in its place is a patch of sky where no light escapes. It is a place you cannot see directly. It's a place you can only understand by the way it moves the universe around it. And it is waiting, perhaps, for millions of years to draw in its next piece of the cosmos. The black hole waits in silence, invisible against the backdrop of space. Around it, stars continue their lives, planets spin in their orbits, and galaxies drift in slow arcs through the universe. Time for the black hole moves as it does for everything else, but from its perspective, the story is very different. Imagine you are far away, watching from a safe distance. You see a star wander too close. Perhaps it was part of a binary pair, and its companion's death in a supernova sent it tumbling through space. Now, the pull of the black hole has caught it. As the star approaches, gravity begins to stretch it. The side closer to the black hole feels a stronger pull than the far side. The star distorts, elongating like a drop of water falling in slow motion. In its final moments, the star is torn apart. Streams of gas spiral into the accretion disk, heating to millions of degrees. From across the cosmos, we might detect this as a flare of X-rays, the final light of a star being unmade. Over time, these meals can make a black hole grow. In crowded regions of galaxies, black holes may encounter enough material to gain mass rapidly. In quieter places, they can go for millions of years without feeding, waiting in the darkness until something strays too close. But even in their quiet phases, black holes are far from inactive. Their gravity shapes the space around them. Light bends in their presence, creating gravitational lensing, a natural telescope that can magnify and distort the view of background objects. We have used this effect to study distant galaxies, their light bent by massive black holes billions of light years away. And then there is the most extreme case, when two black holes meet. This does not happen often, but when galaxies collide, their central black holes can end up orbiting each other. The dance is slow and drawn out, lasting millions of years. Each orbit sends ripples through spacetime, gravitational waves that spread outward at the speed of light. In 2015, for the first time, humans detected these waves. Two black holes, more than 1 billion light-years away, spiraled together and merged, releasing more energy in a fraction of a second than all the stars in the observable universe combined. But not in light, in the invisible undulations of spacetime itself. The merger produces a single, larger black hole. It is a quiet ending to a long dance, leaving no trace but the gravitational waves that have already passed us by. As we drift closer in our imagination toward the event horizon of a black hole, strange things begin to happen. From far away, you could watch an object fall toward it. You would see it slow down, moving more and more slowly as it neared the horizon. Its light would become redder and dimmer until it vanished entirely. From the falling object's perspective, though, time feels normal. It would cross the event horizon in seconds, with no clear boundary to mark the moment. But once inside, there is no way back. Every path through space now leads inward, toward the singularity. This is where our understanding falters. The singularity is a place where our equations break down. General relativity, which describes gravity and the shape of space-time, says the density is infinite. Quantum mechanics, which governs the smallest scales, cannot describe such a point. We need a theory of quantum gravity to know what truly happens there, but we do not have it yet. Some physicists think the singularity might not be a point at all, that quantum effects might spread it out or replace it with something entirely different. Others suspect that information, which we think of as indestructible, might somehow escape the black hole over vast stretches of time. This leads us to one of the strangest ideas about black holes, that they might not be entirely black. In the 1970s, Stephen Hawking showed that quantum effects near the event horizon should cause black holes to emit a faint glow. This Hawking radiation is unimaginably weak for large black holes. But over incomprehensible timescales, it means that black holes can slowly lose mass. The process is glacially slow. A black hole with the mass of our Sun would take about 10 years to evaporate, far longer than the current age of the universe. But in the far, far future, when the stars have burned out and galaxies have faded, Hawking radiation will be the final whisper of black holes into the dark. As the black hole shrinks, the radiation becomes more intense. In its last moments, it releases a burst of energy, then disappears completely. The darkness that was once a trap for everything becomes empty space once more. From birth in the heart of a dying star to death in a flash of Hawking radiation. The life of a black hole spans timescales so vast they are almost beyond human comprehension. They are not eternal, yet they are among the most enduring objects in the cosmos. And yet, their story is still incomplete. There may be black holes that formed in the earliest moments of the universe. Primordial black holes. Born not from stars, but from the collapse of dense regions in the young cosmos. These could be tiny, evaporating quickly, or massive, still roaming the universe today. We do not know if they exist, but if they do, they may be clues to the nature of dark matter, the invisible substance that makes up most of the universe's mass. In this way, black holes are both an end and a beginning. They are the graves of stars, but they may also be the seeds of galaxies. They are the places where our theories fail, yet they might hold the key to uniting the laws of the large and the small. As we float here at the edge of the event horizon, the pull is irresistible. Not just the pull of gravity, but the pull of mystery. To look at a black hole is to look at the limits of our knowledge, to see where the map of physics ends and the unknown begins. In the distance, galaxies drift like islands in an endless sea. Somewhere in each one, there are black holes, waiting silently, shaping the fate of their surroundings without a sound. In almost every galaxy we've ever looked at closely enough, there's something hiding in the center, a supermassive black hole. These giants are millions, even billions, of times the mass of our Sun. They are not simply larger versions of stellar black holes. They are creatures of a different order, forged in ways we still do not fully understand. Some might have formed from the collapse of the very first massive stars, merging and growing over billions of years. Others might have started small, but in the dense hearts of young galaxies. They consumed enough gas, dust, and stars to grow quickly. However they came to be, their presence has shaped the galaxies around them in profound ways. A supermassive black hole does not simply sit in the center like an anchor. When it feeds, it can outshine the rest of the galaxy. Gas falling toward the event horizon forms an accretion disk, a swirling, flattened whirlpool of matter moving at a significant fraction of the speed of light. Friction in this disk heats the gas to extreme temperatures, causing it to radiate energy across the electromagnetic spectrum. These luminous centers are called quasars. For a galaxy with a feeding black hole, the quasar phase can be so bright that it overwhelms the combined light of hundreds of billions of stars. From billions of light years away, we can detect these beacons as they were in the young universe. When galaxies were still assembling, But the energy released doesn't simply shine into the void, it pushes back. Powerful jets accelerated along the black hole's spin axis can launch streams of plasma into intergalactic space. These jets can be millions of light years long, shaping the gas in and around galaxies. In some cases, they can blow away the very material that would otherwise form new stars, slowing or even halting star formation for millions of years. This interplay, the feeding of the black hole, the outpouring of energy, the shaping of galaxies, is known as feedback. It is one of the keys to understanding how galaxies evolve. Without it, our models predict far more stars than we actually observe. With it, the universe makes more sense. And yet, black holes are not constant engines. A galaxy's central black hole can go quiet for eons, only to flare to life when a new supply of gas or stars finds its way inward. The Milky Way's own central black hole, Sagittarius A*, is quiet today, but evidence in the surrounding gas suggests it was more active in the past. We live in a calm neighborhood now, but the potential for violence is always there. Closer to the event horizon, the details become stranger still. The accretion disk is not just a smooth, bright surface. It is a turbulent, chaotic place. Magnetic fields twist and reconnect, accelerating particles to high energies. X-rays and gamma rays are produced in flares, flickering on timescales of minutes or even seconds for smaller black holes, and hours or days for the giants. To truly picture what's happening, you have to imagine a place where gravity is so strong that space itself curves sharply. The photons leaving the disk are bent around the black hole, some looping back into the disk itself, others making their way toward us, but taking a curved path through warped space. This bending means that we can see parts of the disk that should be hidden. Light from the far side arcs over the top, creating a strange, distorted image. When scientists captured the first image of a black hole shadow in 2019, what they were really seeing was this effect. The dark center was not the event horizon itself, but the silhouette of the photon sphere, the region where light orbits the black hole. Around it was the bright ring of the accretion disk, its shape warped by gravity. Seeing that image was like looking into the heart of an idea that had existed for over a century. The equations of Einstein's general relativity had predicted black holes. But to have their shadows photographed, to see their influence etched in light, made them feel more real. From this place of extreme gravity, the conversation sometimes drifts to more speculative ground. Could a black hole be a gateway? Could there be something on the other side? In the mathematics of general relativity, there are solutions that describe not just black holes, but also their time-reversed counterparts, white holes. A white hole would be a place where nothing can enter, only leave. In theory, a black hole and a white hole could be connected, forming a kind of tunnel through space-time. A wormhole. The idea is seductive. Travel through a wormhole, and you could emerge not just in another place, but perhaps in another time. Science fiction has embraced it, imagining ships plunging into black holes and emerging somewhere else entirely. In reality, it's not so simple. Wormholes, if they exist, may be unstable, collapsing too quickly for anything to pass through. They might require exotic forms of matter with negative energy to hold them open. And even if they could exist, the violence of the environment near a black hole would almost certainly destroy anything trying to enter. Still, the equations allow the possibility, and as long as they do, we cannot entirely rule it out. Black holes, after all, have already surprised us more than once. In our own galaxy, there are thought to be millions of stellar mass black holes, and perhaps thousands of intermediate mass black holes, a category between the stellar and supermassive extremes that we have only recently begun to find evidence for. These may form when large clusters of stars merge, or from the collapse of especially massive stars. The smallest known black holes are only a few times the mass of the Sun, while the largest we've found so far are tens of billions of times the Sun's mass. Between them lies an incredible range of scales, each with its own stories of formation, growth, and death. But all black holes share one destiny. They are temporary. No matter their size, Hawking radiation will eventually bring their existence to an end. For a stellar mass black hole, that end lies so far in the future that the universe itself will be unrecognizable by then. For the supermassive giants, their lifetimes are even more vast, outlasting the galaxies that once fed them. In that far, dark future, when the stars have gone out and the last remnants of matter drift in the cold, black holes will be the final monuments of the cosmos. Their slow evaporation will be the last act of a universe that began in fire and ends in silence. It is strange to think of them as dying, these objects that seem so eternal. But perhaps that is part of their fascination. They are reminders that even the mightiest things in the universe are not beyond the reach of time. And until that distant end, they will continue to shape the cosmos, their presence felt in the dance of galaxies, the flares of quasars, and the silent pull on the space around them. They are, in a way, the universe's most patient storytellers. Imagine drifting toward one. You've seen the swirling disk of gas around it from a safe distance, but now you are close enough to feel its pull directly. At first, nothing seems different. Space, after all, is mostly empty. But as you approach, that emptiness feels heavier, more inevitable. Gravity is not simply stronger here, it is changing across your body. Your feet, being closer to the black hole, feel a greater pull than your head. The difference grows with every kilometer you descend. This stretching effect has a grim name: spaghettification. For a small black hole, the tidal forces that cause spaghettification become overwhelming far from the event horizon. If you were falling feet first, your body would be stretched into a long, thin shape, your spine pulled apart, your cells elongated, even your molecules feeling the strain. No material we know of can resist this much difference in gravitational pull. You wouldn't survive long enough to see the event horizon up close. But for a supermassive black hole, the story changes. The event horizon is so far from the central singularity that the difference in gravitational pull across your body might be negligible. You could cross that boundary without any violent stretching, without even noticing the precise moment you passed it. From your perspective, you would simply be falling into a place that grew darker and more strange with every second. From the outside, though, it's a different picture. Anyone watching you fall toward the event horizon would see you slowing down, moving more sluggishly as you approached. Light from you would be stretched to longer and longer wavelengths, your colors fading toward red, then disappearing into invisibility. Time itself would appear too slow for you from their perspective. You would never quite seem to cross the event horizon. Instead, you would fade, becoming dimmer, redder, until you vanished entirely. From your point of view, however, you would cross in finite time, continuing your fall toward whatever lies within. And here the mystery deepens, because what lies inside a black hole is not something we can observe. The equations of general relativity tell us that at the very center, all the mass is crushed into a point of zero volume, a singularity. Where density is infinite and the known laws of physics break down, this singularity is hidden from the universe by the event horizon. Information from inside cannot escape. Nothing can tell the outside what is happening there. This is not just a practical limit, but a fundamental one. The horizon is a one-way membrane. What happens to matter as it approaches the singularity? The mathematics suggest that space-time is so warped that all paths lead inward. There is no standing still, no turning back. The dimensions of space collapse. Forward in time becomes indistinguishable from forward in space. Every particle's future ends in the same place, the singularity. But some physicists suspect the singularity is not a literal point. Instead, they believe it is a sign that our current theories are incomplete. At these extremes, quantum mechanics should matter as much as gravity. Yet our two great theories do not agree here. The quest to reconcile them. To find a theory of quantum gravity is in part a quest to understand what really happens inside a black hole. String theory, loop quantum gravity, and other approaches all offer possibilities, but no consensus has emerged. It is as if the universe has placed its deepest secret inside a vault that no experiment can open. This leads to one of the strangest puzzles in modern physics, the black hole information paradox. According to quantum mechanics, information about a physical system, the arrangement of its particles, their states can never be destroyed. But black holes seem to violate this rule. If you throw a book into a black hole, the matter is lost from the outside world. Over eons, the black hole emits Hawking radiation, shrinking and eventually evaporating. But Hawking radiation appears to be purely thermal. It carries no information about what fell in. That would mean the information in the book is gone forever. And yet, this kind of loss would break the fundamental principles of quantum theory. So the paradox stands. Does the information vanish, or is it somehow preserved? Some suggest that the information is encoded in subtle correlations in the Hawking radiation. Others propose that it remains smeared across the event horizon, like a hologram, a possibility tied to the holographic principle, which suggests that the universe itself may be describable as information on a lower dimensional surface. Whatever the answer, it forces us to think differently about reality. Black holes are not just objects in space, they are testing grounds for our deepest theories. They push our ideas to the breaking point. For the traveler falling in, though these questions are academic, once past the event horizon, the pull of gravity allows no escape. Even light, the fastest thing in the universe, cannot climb out. Your fate is to move inward. Your remaining time measured not in years or hours, but perhaps in seconds, depending on the size of the hole. The path to the singularity may be calm at first, but as you approach, tidal forces rise again. Even in a supermassive black hole, the interior is finite. You cannot fall forever inside it. Eventually, the differences in gravitational pull across your body grow immense. You are stretched, squeezed, and finally compressed into whatever form matter takes when space-time itself collapses. No signal from you reaches the outside world. From the perspective of the rest of the universe, your story ended when you touched the horizon. Inside, you have experienced a final chapter no one else will ever read. In some speculative scenarios, your story might not end entirely. Certain models of quantum gravity suggest that the singularity could be replaced by something else, perhaps a bounce where matter is repelled at extreme density and spat into another region of spacetime. If so, the inside of a black hole could be connected to another universe. But these are ideas without evidence, dreams woven from mathematics and curiosity. The truth is that for now, the interior of a black hole remains the most private place in the cosmos. And outside, life goes on. Black holes move through galaxies like ghosts, unseen until their gravity disturbs something nearby. A star wandering too close may be torn apart in a tidal disruption event, its gas forming a temporary accretion disk that flares brightly before fading. A binary system with a black hole and a normal star can produce X-ray bursts, as matter from the star is siphoned into the hole. We detect black holes by their effects: the motion of nearby stars, the radiation from accretion disks, the ripples of gravitational waves when to merge. In 2015, LIGO detected such ripples for the first time, a tiny vibration in space-time itself, caused by the merger of two black holes over 1 billion light-years away. That signal was not light, but gravity speaking directly to our instruments. It was as if the universe had sent a faint, deep tone from a distant, unseen orchestra. With gravitational wave observatories now operating regularly, we have a new sense with which to study black holes. These detections have already expanded our picture of them. We have found black holes heavier than any stellar remnants we expected, and systems in which they merge more often than our old models predicted. The population of black holes is richer and stranger than we thought. And this is just the beginning. Long before humans looked up at the night sky and wondered, black holes were already shaping the universe. They may have been among the first structures to influence the newborn cosmos after the Big Bang. Some formed almost instantly, primordial black holes. If they exist, these would have been born from density fluctuations in the very early universe, mere fractions of a second after its birth. Unlike stellar black holes, which form from collapsing stars, primordial black holes could be of any size, from microscopic to planetary mass. We have yet to find direct evidence for them, but if they do exist, they might account for some of the universe's elusive dark matter. Tiny ones would have evaporated long ago through Hawking radiation, but larger ones could still be drifting quietly through space today. Invisible unless they happen to interact with nearby matter. Then, as the first generation of massive stars lived and died, stellar black holes began to appear. These were relatively small, just a few times the mass of the Sun, but they set the stage for something greater. Over millions of years, gravity pulled matter together into galaxies. In the hearts of these galaxies, black holes grew, some becoming supermassive, millions or billions of times the mass of the Sun. We still don't fully understand how they became so large so quickly, but their presence shaped the galaxies around them. A supermassive black hole at a galaxy's center is not just a silent occupant. When it feeds, it can become one of the most luminous objects in the universe. A quasar, matter falling into the central black hole, can release more energy than all the stars in the galaxy combined, outshining everything else. Jets of charged particles accelerated to near light speed can erupt from the poles of the accretion disk, shooting out for thousands or even millions of light years. These jets can heat and stir vast regions of intergalactic gas, influencing star formation far from the black hole itself. So in a way, black holes help decide the pace of galactic evolution. They are both destroyers and creators, regulating how galaxies grow, shaping the cosmic web. But their lives are not static. Black holes can move, especially after collisions. When galaxies merge, their central black holes spiral toward each other, dancing a slow, tightening orbit. Over millions of years, they draw closer, losing energy through gravitational waves. Eventually, they merge in a burst of space-time ripples, sending waves of gravity outward across the universe. The energy released in these moments is staggering. For a brief instant, a black hole merger can outshine all the stars in the observable universe, not in light, but in gravitational waves. These waves stretch and squeeze space itself as they pass, imperceptible to us, but detectable with the right instruments. The LIGO and Virgo observatories have already recorded dozens of such events. Each detection is like catching the faint echo of a cosmic drumbeat, a sign that somewhere in the dark, two titans have become one. The merged black hole is heavier than either of its parents, but not as heavy as their masses combined. Some of the mass has been converted directly into gravitational energy. This process allows black holes to grow over time, building larger and larger structures. We have even seen evidence of black holes merging in the distant past, back when the universe was less than half its current age. This means they have been shaping the cosmos for billions of years, working quietly in the background while stars were born, lived, and died. But like everything else in the universe, black holes are not immortal. Stephen Hawking's groundbreaking work in the 1970s revealed that they are not entirely black. Quantum effects at the event horizon cause them to emit a faint glow. Hawking radiation. This radiation is not like the light from stars. It is incredibly weak, so faint that for stellar and supermassive black holes, it is undetectable with current technology. But it carries away energy, which means it carries away mass. Over unimaginable timescales, this process causes a black hole to shrink. The smaller it gets, the faster it evaporates, until, in its final moments, it releases a last powerful burst of energy. For stellar black holes, This process takes vastly longer than the current age of the universe, far beyond the lifetime of all the stars we know. But in the deep future, when galaxies have grown cold and empty, black holes will be among the last active objects left. They will slowly fade, one by one, until the universe is quiet. The final black holes to die will be the supermassive ones, their evaporation stretching out to timescales of 101,0010, 110,100 years or more, a number so large it escapes ordinary comprehension. In that era, the cosmos will be a place without light, without stars, without heat. Only the faint final whispers of black hole radiation will disturb the silence. Eventually, even that will cease. Some physicists suspect this is the ultimate fate of our universe. The heat death, where all energy is evenly distributed and no structure remains. Black holes will have been the last to fall, the final monuments to a universe that once blazed with galaxies and life. But there are other possibilities. The universe is not destined for eternal expansion. It might one day contract, reversing its growth in a big crunch. Or, if dark energy changes in the far future, the cosmos could end in a big rip, tearing apart galaxies, stars, planets. And even atoms before black holes have time to fade. These ideas are speculative, and the truth is, we do not know. The end of black holes, like their beginnings, remains partly hidden from us. What we do know is that they are not merely destructive anomalies. They are central characters in the story of the universe, playing a role in its structure, its history, and possibly even its ultimate fate. To think of black holes only as cosmic vacuum cleaners is to miss their deeper significance. They are reminders of how strange the universe can be, how far the rules of physics can be stretched. They challenge our understanding and invite us to imagine beyond the boundaries of what we can see. And they are beautiful in their own dark way. The image of a black hole shadow, captured in 2019 by the Event Horizon Telescope, was a triumph of science and human cooperation. It showed the silhouette of the event horizon against the glowing ring of its accretion. Disk, the first time we had ever seen such a thing directly. That image is a kind of promise. There is more to learn, more to see, more to understand. Black holes, once purely theoretical, are now real places in our mental map of the universe. We know where some of them are. We can study their effects. We can listen to their mergers. But their deepest secrets remain locked away beyond the event horizon. We can only stand outside, looking at the boundary, imagining what lies within. And perhaps that is part of their power. They are mysteries we cannot touch, forces we cannot tame, questions we cannot yet answer. They are a reminder that the universe is not ours to command, only to explore, to wonder at, to try to understand. Approaching a black hole is unlike approaching anything else in the universe. As you draw closer, you begin to feel the warping of space and time itself. From a safe distance, its gravity feels strong but not impossible to resist, much like orbiting a massive star. But once you get too close, the pull becomes overwhelming, curving space-time so sharply that no escape is possible. This point of no return is the event horizon. To an observer far away, time near the event horizon appears to slow down. A spacecraft falling toward the black hole would seem to approach the horizon more and more slowly, its clock ticking at a fraction of the speed of ours. From our perspective, it would never actually cross the horizon. Instead, it would freeze in place, fading into darkness as its light is stretched into longer and longer wavelengths. But for the crew inside that spacecraft, time would seem perfectly normal. They would cross the event horizon in seconds, not noticing anything physically unusual at that exact point. Once inside, however, every possible path through space leads deeper toward the singularity at the black hole's center. That singularity, if it exists as we think, is a place where our understanding of physics breaks down. Matter is crushed into infinite density, and space-time curves infinitely. But infinite is just a sign that our equations can no longer describe reality there. Quantum gravity, the still unknown theory that unites general relativity with quantum mechanics, might reveal a different picture entirely. The journey inside is not the same for every black hole. For a small stellar mass black hole, the tidal forces, the stretching and squeezing caused by extreme differences in gravity, would be lethal long before you reached the singularity. Your body, your spacecraft, everything would be pulled apart in a process scientists call spaghettification. But for a supermassive black hole, the story changes. Its event horizon is so large that the tidal forces at the horizon could be mild enough for you to pass through unharmed. You could, in theory, cross into its interior and survive for a while, falling toward the singularity. What you would see inside is unknown and perhaps unknowable, because no signal can escape to tell the tale. This strange behavior of time near black holes connects them to another deep concept: entropy. Entropy is a measure of disorder, or, more precisely, the number of possible microscopic arrangements of a system. In everyday life, it's tied to the arrow of time. Entropy tends to increase, which is why we remember the past, but not the future. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered something remarkable. Black holes have entropy. In fact, their entropy is proportional to the surface area of their event horizon, not their volume. This is counterintuitive. Most physical systems have entropy related to how much space they take up. But black holes break that rule. This led to the idea that the information content of a region of space might be stored on its boundary, a concept known as the holographic principle. It's as if the universe itself could be a kind of projection, with the true information encoded on a distant surface. The entropy of a black hole is enormous, far greater than the entropy of the stars, gas, and planets that might have formed it. This suggests that black holes are the ultimate entropy machines, driving the universe toward maximum disorder. But there's a puzzle here. What happens to the information about the things that fall in? In classical physics, anything that crosses the event horizon is lost forever. But in quantum mechanics, information cannot be destroyed. This is the black hole information paradox, one of the biggest unsolved problems in theoretical physics. Some theories suggest that information might be somehow encoded on the event horizon and released slowly through Hawking radiation as the black hole evaporates. Others propose that new physics, perhaps wormholes or quantum remnants, might be needed to resolve the paradox. And speaking of wormholes, there's a fascinating speculative link between them and black holes. In theory, certain kinds of black holes, paired with exotic matter that has negative energy density, could be connected to another place in the universe, or even another universe through a stable wormhole. This idea is deeply hypothetical and faces major challenges, not least the fact that exotic matter has never been observed in sufficient quantities. But in science fiction, wormholes are a favorite way to turn black holes from deadly traps into cosmic shortcuts. Advanced civilizations, if they exist, might even use black holes as tools. A spinning black hole contains enormous amounts of rotational energy. In principle, this could be extracted using processes like the Penrose mechanism, in which matter is dropped into the ergosphere, a region just outside the event horizon where space-time itself is dragged around by the black hole's rotation. By carefully arranging the trajectory of that matter, an object could escape with more energy than it entered with, stealing a bit of the black hole's spin. This is purely theoretical for us today, but for a civilization capable of engineering on cosmic scales. Black holes could be power plants, time machines, or even starships. Some scientists have proposed that supermassive black holes could serve as meeting points for civilizations across the galaxy, both because they are stable for billions of years and because they are gravitational landmarks visible from great distances. If life is rare but long-lived, perhaps one day such places will become hubs of communication and travel. Even without alien engineering, black holes already serve as cosmic laboratories. They let us test general relativity under extreme conditions, probe the behavior of matter at nuclear densities, and explore the limits of quantum theory. Every gravitational wave detection, every X-ray flare from a feeding black hole, is a new data point in our quest to understand the universe. Our own galaxy, the Milky Way, harbors a supermassive black hole at its center, Sagittarius A*. It is about 4 million times the mass of the Sun, but quiet most of the time, only occasionally flaring as it swallows bits of gas and dust. We know it's there because we can watch stars in its vicinity tracing tight, fast orbits around an invisible point. If you could travel there, you would see a cluster of brilliant stars whipping around in a space barely larger than our solar system, moving at thousands of kilometers per second. Beyond them lies the glowing ring of material falling toward the event horizon, and within that, darkness. Someday, our descendants, if humanity survives, might venture close enough to study Sagittarius A* directly, perhaps sending probes to skim the edge of the event horizon. Such missions would not return in the usual sense, but the data they sent back could reshape our understanding of reality. Black holes are not just astrophysical objects. They are doorways to the limits of physics, to questions about time, space, and existence itself. And in their silent, invisible pull, they remind us that the universe is stranger than we can easily imagine. Black holes do not live in isolation from the rest of the cosmos. They are woven into the story of galaxies themselves. In fact, the growth of galaxies and the growth of black holes appear to be deeply linked, almost like dance partners that have been moving together since the earliest times. At the center of almost every large galaxy we've observed, there's a supermassive black hole. Some are relatively quiet, like the one in the Milky Way. Others are ferociously active, consuming gas and dust at such a rate that they outshine all the stars in their galaxy combined. These are known as quasars, and they were much more common in the early universe. When a supermassive black hole is actively feeding, the material spiraling and forms an accretion disk, a whirling, superheated disk of plasma that can reach millions of degrees. Friction and magnetic fields within the disk cause it to emit incredible amounts of light across the spectrum, from X-rays to visible light to radio waves. Some of this energy also escapes as jets, narrow beams of particles and radiation that can extend for thousands or even millions of light years. These jets punch into intergalactic space, heating the surrounding gas and sometimes preventing it from cooling enough to form new stars. This is one way black holes regulate the growth of galaxies. When the central black hole feeds too greedily, it blasts out so much energy that it effectively turns off star formation, leaving the galaxy to grow old and red. The relationship between black holes and galaxies is visible in the so-called M-sigma relation, a correlation between the mass of a galaxy's central black hole and the velocity of the stars in its bulge. This suggests that somehow, even though the black hole is tiny compared to the galaxy, the two influence each other's evolution over billions of years. Some scientists suspect that without supermassive black holes, galaxies might look completely different, perhaps bloated with too many stars, or lacking the structure we see today. In this way, black holes are not just destroyers. They are cosmic architects. But not all black holes are born from the death of stars or from the slow growth of supermassive ones. There is a possibility that some black holes were born in the very first moments after the Big Bang. These are called primordial black holes in the chaotic, ultra-dense early universe. Regions of slightly higher density could have collapsed directly into black holes without forming stars first. These could be tiny, with masses smaller than mountains, or as massive as thousands of suns. If they exist, primordial black holes could be an explanation for some of the mysterious dark matter that makes up most of the universe's mass. Because they would be small and cold, they would be nearly invisible, unless They passed in front of a distant star or emitted the final burst of radiation at the end of their lives. This brings us to the death of black holes, a process that, for most, is unimaginably slow. In 1974, Stephen Hawking combined the principles of quantum mechanics with general relativity and discovered that black holes are not entirely black. They emit a faint radiation, now known as Hawking radiation, caused by quantum effects near the event horizon. Over immense timescales, this radiation slowly saps energy from the black hole, causing it to lose mass. For stellar mass black holes, this process takes far longer than the current age of the universe. But for tiny black holes, such as the hypothetical primordial ones, evaporation could happen within billions or even millions of years. As a black hole shrinks, it radiates faster in a runaway process that ends in a final burst of high-energy radiation. In the far, far future, when all the stars have burned out and galaxies have gone dark, black holes will be the last major objects remaining. Slowly, over unimaginable eons, even they will fade away. The death of the last black hole would mark the end of structure in the universe. From then on, the cosmos would be a thin, cold soup of particles and radiation expanding forever. This is one vision of the far future, the heat death where no energy gradients remain to power complexity or life. But there are other possibilities. Some physicists speculate that the evaporation of black holes could release the information they have swallowed, resolving the information paradox and perhaps seeding new universes. In certain models of cosmology, the death of a black hole might cause a bounce into another region of spacetime, a kind of cosmic recycling that could keep existence going forever in some form. If this sounds speculative, that's because it is. We are standing at the edge of what we know, peering into a darkness we cannot yet illuminate. Black holes are both the most extreme testbeds for our theories and the biggest hints that those theories are incomplete. Even their basic nature may be stranger than we think. Some researchers suggest that what we call black holes might be fuzzballs, massive tangles of strings from string theory, with no singularity at the center. Others imagine them as gravastars, filled with exotic quantum states of matter. In these models, the event horizon might behave differently, potentially allowing for subtle leaks of information. Observationally, we have only just begun to see black holes directly. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, the supermassive black hole in the galaxy M87. That image showed a bright ring of light bent by the black hole's gravity, surrounding a dark central region where the event horizon lies. This was not just a technological triumph, it was a profound moment in science, giving us a visual connection to something that had been purely theoretical for more than a century. The EHT has since imaged Sagittarius A*, our own galaxy's central black hole. And future upgrades will sharpen these images and allow us to watch changes in real time. As our tools improve, from gravitational wave observatories to high-resolution radio telescopes, we will learn more about how black holes grow, merge, and interact with their surroundings. Every new piece of data helps refine our theories, bringing us closer to a complete understanding. Yet perhaps the most powerful thing black holes give us is perspective. They remind us that the universe is not built for our comfort or comprehension. It contains extremes of density, time, and energy that stretch our minds and our equations alike. And still, here we are, tiny creatures on a small planet able to imagine these extremes, to calculate their properties, to send instruments across the void to detect their whispers. Black holes are the silent hearts of galaxies, the engines of quasars, the forges of gravitational waves. They are the cosmic storytellers of birth, growth, and eventual fading into the dark. And they are the mirrors in which we see the limits of our own knowledge. In their depths may lie answers to the deepest questions we can ask. What is time? What is space? Is information ever truly lost? And can the universe recycle itself through these mysterious dark gates? We do not yet know. But as long as there are minds to wonder, we will keep looking into the darkness, listening for the echoes of what lies within. When two black holes meet, the universe listens. For billions of years, they may orbit one another in a slow spiral, losing a tiny fraction of their energy with every pass. Most of the time, that energy loss is negligible, but as they draw closer, the pace quickens. Space itself begins to tremble with their dance. Eventually, in the final seconds, they are moving at half the speed of light, the gravitational pull between them almost unimaginable. Then, in one last breathtaking moment, they collide, merging into a single, larger black hole. The event sends ripples of space-time, gravitational waves, racing outward in every direction. In 2015, scientists detected such a signal for the very first time. It lasted only a fraction of a second, a faint chirp buried in the noise of LIGO's detectors. But that chirp was the sound of two black holes, each about 30 times the mass of the Sun, merging over 1 billion light-years away. This was one of the most important discoveries in modern astrophysics. Not only did it confirm a prediction of Einstein's general relativity, it also opened an entirely new way of observing the universe. With gravitational waves, we are no longer limited to detecting light. We can feel the ripples in the very fabric of space-time. Since then, dozens of black hole mergers have been recorded. Some involve pairs of stellar mass black holes. Others are more surprising, like the mergers between black holes and neutron stars, or the detection of unusually massive black holes that challenge our theories of how such objects form. Gravitational wave astronomy is still young. In the coming decades, more sensitive detectors on Earth and in space will allow us to pick up smaller signals from farther away and with much more detail. This will give us a clearer view of black holes, not just as solitary objects, but as participants in a cosmic network of interactions. It's possible we will one day detect the merging of two supermassive black holes, a cataclysm that would shake the universe on scales we can barely imagine. These events may occur when galaxies collide, their central black holes eventually finding one another and beginning their slow spiral. And yes, galaxies do collide. Our own Milky Way is on a collision course with the Andromeda Galaxy, due to meet in about 4 billion years. The black holes at their centers will eventually merge, producing a gravitational wave so immense it will echo across the observable universe. But even without such cosmic violence, black holes can reveal themselves in quieter, stranger ways. Sometimes, a black hole passes close enough to a star to strip matter from it. The gas spirals inward, heating to extreme temperatures, producing bursts of X-rays. These events, called tidal disruption events, give astronomers a fleeting glimpse of a black hole's appetite in action. On rare occasions, we've caught a black hole devouring a star so completely that it produced an eruption bright enough to be seen across billions of light-years. In such moments, the black hole is briefly one of the brightest objects in the universe, before fading back into the shadows. And then there are the possibilities we can only guess at. Could black holes harbor entire universes within them? Could their interiors, hidden from us forever, follow entirely different laws of physics? If the event horizon is a boundary beyond which nothing escapes, might it also be a gateway, in some sense, to somewhere else? These ideas remain speculative, but they touch on something essential. Black holes are as much philosophical puzzles as they are physical ones. They challenge our intuitions about time, space, and causality. For example, near a black hole, time itself behaves strangely. To a distant observer, an object falling toward the event horizon appears to slow down. Approaching the edge ever more slowly, its light stretched into redder and redder wavelengths until it fades completely. From the object's own point of view, it crosses the horizon in a finite time, experiencing whatever fate awaits inside. This difference is not a trick of perception. It's built into the geometry of space-time. In the presence of extreme gravity, space and time become deeply intertwined. and the rules we live by in our everyday experience simply do not apply. For some, this is unsettling. For others, it's exhilarating. A reminder that reality is deeper, stranger, and more complex than we can see with our eyes alone. Our technology is now allowing us to explore this strangeness more directly. Space telescopes can watch the regions around black holes with incredible precision, tracking the flickering of X-rays from the inner edges of accretion disks. Radio arrays can map the jets that blast outward at nearly light speed. And yet, for all these advances, we remain in the earliest stages of understanding. Black holes are the great unfinished chapter in our story of the universe, the part where the plot twists into something we can barely follow. We do know this. Black holes have been shaping the cosmos for as long as there has been structure. They may have helped ignite the first bursts of star formation, regulated the growth of galaxies, and perhaps even determined the conditions for life to emerge. It is possible that our own existence, our planet, our star, our very bodies owes something to the quiet influence of black holes over billions of years. And when we are gone, they will still be here, silent and patient, watching the universe change around them. One day, far into the future, black holes will be the last luminous things in the cosmos. Not because they shine themselves, but because they will be the final sources of radiation in an otherwise cold and dark universe. Over unimaginable spans of time, they will evaporate through Hawking radiation, each ending in a brief flash of light before fading forever. The largest black holes will take 10,100 years or more to vanish, a number so vast that our human minds cannot truly grasp it. This is the ultimate life cycle of a black hole, born from death, growing through consumption, shaping its surroundings, and eventually fading away into nothingness. Yet, in that fading, there may be the seeds of something new. Some theories suggest that black holes could connect to other regions of spacetime, or even to entirely new universes. If that is true, then perhaps the death of a black hole is not an ending, but a kind of birth, the passing of a spark into another realm. Whether or not this is the case, black holes remain symbols of the unknown. They mark the places where our theories break, where our understanding falters, and where mystery still rules. And maybe that is their greatest gift to us. The reminder that there is always more to learn, that curiosity can carry us deeper into the dark, and that even in the deepest night, we can still find wonder. We've talked about stellar mass and supermassive black holes, the ones we've detected, the ones we've seen indirectly through their influence on matter and light. But physics leaves room for stranger possibilities. One of these possibilities is the primordial black hole. Unlike those born from collapsing stars, primordial black holes could have formed in the very early universe, within the first fractions of a second after the Big Bang. In that young cosmos, matter was not evenly spread. Tiny fluctuations in density, seeds that would one day grow into galaxies, rippled through space. If a fluctuation was intense enough in a small enough region, gravity could have crushed it into a black hole almost instantly. These black holes could be as small as mountains or as massive as planets, or even heavier. Some could have masses far below what we expect from stellar collapse, down to the mass of a single asteroid. The smallest of these would have been devoured by Hawking radiation long ago, but the slightly larger ones could still be drifting through the universe today, almost impossible to detect. If they exist, they could make up some or all of the mysterious dark matter, the invisible mass that outweighs all visible matter in the universe 5-to-1. The idea is tantalizing. Countless tiny black holes left over from the dawn of time, shaping galaxies and clusters through their hidden gravity. We don't know if primordial black holes are real. Astronomers have searched for their telltale signs, like the brief brightening of distant stars as such a black hole passes in front, bending its light. So far, the results are inconclusive. Still, the search continues. Because if primordial black holes do exist, they could open an entirely new window into the earliest moments of the universe, a time we cannot see with light alone. And speaking of strange black holes, there is another category we can imagine but have not yet seen: intermediate mass black holes. These would be heavier than stellar black holes, but lighter than the giants in galactic centers. Somewhere in the range of hundreds to hundreds of thousands of solar masses. They might form when massive stars merge or when dense clusters of stars collapse together. Finding them has proven difficult. A few candidates have been spotted, often in the hearts of dense star clusters or in unusual X-ray sources, but confirming their existence is tricky. They're like shadows on the edge of vision, hinted at but not yet nailed down. If we do find them in large numbers, they could help us understand how supermassive black holes get their start. Maybe the giants we see today grew from such seeds, feeding for billions of years until they became the monsters that anchor galaxies. Of course, black holes are not just a curiosity for astronomers. They are also a puzzle for physics itself. One of the biggest puzzles is the information paradox. In classical physics, whatever falls into a black hole is gone forever. The event horizon is a one-way surface. Once you cross it, no signal can escape. The details of what fell in the arrangement of particles, the patterns of their states, are lost to the outside universe. But in quantum physics, information cannot be destroyed. The exact state of a system may change, but the underlying information is preserved in some form. When Stephen Hawking discovered that black holes radiate, it seemed to suggest they could evaporate entirely over time. But if they vanish, where does the information go? Does it simply disappear, violating the laws of quantum mechanics? Or is it somehow encoded in the radiation itself, in a way we don't yet understand? This question has driven decades of debate among physicists. Various solutions have been proposed, from subtle correlations in the Hawking radiation, to exotic firewalls at the event horizon, to the idea that the information is stored on the horizon's surface itself, like a cosmic hologram. This holographic principle has become one of the most intriguing concepts in modern physics. It suggests that the three-dimensional contents of a region of space could be fully described by data encoded on its two-dimensional boundary. If true, this idea might apply not just to black holes, but to the entire universe, a radical rethinking of what space and reality actually are. Black holes may therefore be more than just astrophysical objects. They may be laboratories for understanding the deepest laws of nature, the place where gravity, quantum mechanics, and thermodynamics all collide. Some physicists even wonder if black holes are the key to uniting Einstein's theory of relativity with the quantum world, a unification that has eluded science for nearly a century. If we could solve the mysteries of black holes, we might finally glimpse the foundations of reality itself. And then there are the hypothetical cousins of black holes, objects that may not exist in our universe but are fascinating to imagine. One is the white hole. In theory, a white hole is the opposite of a black hole. Nothing can enter, and matter can only escape. In the equations of general relativity, white holes appear as time-reversed black holes. They could spew out matter and energy, never to take anything in. But they would be unstable, collapsing into black holes the moment anything touched them. We've never seen one, and most scientists suspect they do not occur naturally. Still, in certain speculative models, a black hole in one region of spacetime could be connected to a white hole in another, forming a wormhole. A wormhole is a shortcut through spacetime, linking distant points in space or even different universes. In theory, they could allow faster-than-light travel, at least from the point of view of the traveler. But wormholes are not stable under normal conditions. They would pinch shut almost instantly. To keep one open, you'd need some form of exotic matter with negative energy density, something not known to exist in usable quantities. If black holes do connect to wormholes, could mean that falling into one might not mean certain death, but instead transport to somewhere else, This is more science fiction than science, but it's a reminder that the mathematics of black holes leaves room for astonishing possibilities. And even if no traveler could survive the trip, wormholes, if they exist, might one day be detectable through their gravitational influence or their distortions of background light. Speculation aside, what we know for certain is already incredible. Black holes are born from death. They can merge in cosmic dances. They can warp space and time to extremes, and they may slowly evaporate over unimaginable spans of time. They are the universe's most extreme storytellers, and every one of them is a story written in the language of gravity. And yet, their stories do not end when they die. The energy they release in their final moments, the ripples they send across space-time, the influence they have on galaxies and stars, these effects echo long after the black holes themselves are gone. It's possible that in the far future, when all stars have burned out and all galaxies have drifted apart, the universe will be silent except for the slow whisper of evaporating black holes. That whisper may be the last voice the cosmos ever speaks. And in that silence, perhaps there will still be listeners. Not living creatures like us, but structures of information, patterns of energy, the final inheritors of a universe that began in fire and ended in shadow. Supermassive black holes are in a category all their own. While stellar black holes are the end states of stars, supermassive black holes may be the engines of galaxies. Every large galaxy we've observed seems to have one at its center. The Milky Way's own giant Sagittarius A is about 4 million times the mass of our Sun. In some galaxies, these monsters reach billions of solar masses. How do they get so big? Still a mystery. One idea is that they began as smaller black holes, perhaps formed from the collapse of massive stars, or even from the earliest days of the universe, and then grew over billions of years by swallowing gas, dust, stars, and even other black holes. Another possibility is that they formed directly from the collapse of enormous clouds of gas in the early universe, skipping the stellar stage entirely. If that's true, they could have started life already millions of times the Sun's mass. Whatever their origins, supermassive black holes profoundly shape their galaxies. When they actively feed, they can become quasars, some of the brightest objects in the universe. A quasar's light comes not from the black hole itself, but from the disk of superheated material spiraling into it. As gas falls inward, it collides, compresses, and heats up to millions of degrees, releasing staggering amounts of radiation. Quasars can outshine entire galaxies. Their beams can travel billions of light years, allowing us to see them as they were when the universe was young. But this furious feeding also drives powerful outflows, winds and jets that can sweep across a galaxy, blowing away gas and shutting down star formation. In this way, supermassive black holes can act as both creators and destroyers, triggering bursts of star birth in some places while quenching it in others. It's a delicate balance. Without these central giants, galaxies might look very different. In fact, some studies suggest that the growth of galaxies and their central black holes is tightly linked. That as one grows, so does the other, in a cosmic dance billions of years in the making. And yet, even supermassive black holes are not eternal. Like their smaller cousins, they lose mass through Hawking radiation, but so slowly that for practical purposes, it's negligible. A black hole with the mass of our Sun would take 1,067 years to evaporate. For a supermassive black hole, the timescale is incomprehensibly larger, many orders of magnitude beyond that. For now, the only way a supermassive black hole could die is through collision or disruption. When two galaxies merge, their central black holes eventually spiral together and collide, releasing gravitational waves powerful enough to shake the fabric of space-time itself. These mergers are rare on human timescales, but common over cosmic history. The ripples they produce are the kind of signals that next-generation gravitational wave observatories will detect routinely, mapping the hidden mergers of the universe. But eventually, even these giants will be gone. In the far future, when the last stars have burned out, black holes will dominate the universe. This is the era of black hole cosmology, a time when the only significant sources of gravity are the silent, invisible remnants of collapsed matter. Over unimaginably long spans, they will drift apart as the expansion of the universe accelerates, until each one resides in its own lonely bubble of space-time, cut off from all others. Then, one by one, they will fade. Stellar mass black holes will go first, evaporating in bursts of Hawking radiation, releasing their final store of energy into the cold darkness. Supermassive black holes will linger far longer, but they too will eventually vanish, leaving behind only a thin mist of low-energy photons and elementary particles. By that point, the universe will be unrecognizable. No stars, no galaxies, no planets. Just a vast, dark expanse, expanding forever, with only the faint glow of ancient evaporation marking where giants once slept. This black hole era is a key chapter in the heat death scenario, one of the leading theories for the end of the universe. In it, entropy, the measure of disorder, approaches its maximum, and the cosmos reaches a state where nothing interesting happens anymore. It's a sobering thought, but also strangely beautiful. In this vision, black holes are the last storytellers, the last engines of transformation in a universe winding down. But black holes may also play a role in stranger endings. Some cosmologists speculate about the Big Rip, a future where dark energy, the mysterious force driving cosmic acceleration, grows stronger over time. In this scenario, galaxies, stars, planets, and eventually even atoms are torn apart by the expansion of space itself. In such a universe, black holes would not have the chance to evaporate slowly. Instead, they would be ripped apart along with everything else, their event horizons shredded by the stretching of space-time. Another possibility is the Big Crunch, the reverse of the Big Bang. If dark energy were to change sign or gravity somehow became stronger on large scales, the expansion could halt and reverse. Galaxies would race toward each other. Stars would collide, and temperatures would rise until everything collapsed into a final singularity. In that scenario, black holes might merge into one ultimate black hole, a singularity containing the entire universe, perhaps setting the stage for another Big Bang. These are speculative ideas, but they show how central black holes are to our thinking about the universe's fate. Whether as the last survivors of cosmic time or as participants in its rebirth, they mark the boundaries of what we can imagine. And for all their mystery, we are learning more about them than ever before. The first image of a black hole's shadow, released in 2019 by the Event Horizon Telescope, showed us the silhouette of the supermassive black hole in the galaxy M87. It was a ring of light around darkness, exactly what Einstein's theory predicted, brought to life by human effort and collaboration. In 2022, the same project gave us the first image of Sagittarius, our own galaxy's central giant. These images are not just pictures. They are direct confirmations that the warped space of a black hole is real, that the equations of general relativity hold even in their most extreme regimes. In the coming decades, we will map more black holes, watch matter spiral into them in real time, and catch the ripples of their mergers with unprecedented sensitivity. But some questions may remain forever out of reach. We may never know what lies beyond the event horizon, or how information is truly preserved in the evaporation process. Perhaps that's fitting. Black holes are, after all, cosmic boundaries, not just in space, but in knowledge. They remind us that the universe is not ours to fully grasp, that there are places where our theories break down and our imagination must take over. They are the ultimate teachers of humility. And yet, by studying them, we push the limits of what humanity can know. Even as they hide their secrets, black holes inspire us to keep looking, to keep asking, to keep dreaming. Because in the end, black holes are not just about darkness. They're about transformation, of matter, of energy, of space, of time, and of our own understanding. They are the universe's way of saying, there is always more to discover. Black holes have always existed in the uneasy space between science and imagination. Long before they were confirmed, they lived in the realm of speculation. A sort of myth whispered about in the equations of Einstein and the writings of science fiction authors. To many, they were monsters, cosmic whirlpools that devour anything that strays too close. And in a sense, that's true. Cross the event horizon, and there is no escape. But the reality is more complex. Black holes are not vacuum cleaners indiscriminately sucking in their surroundings. A black hole with the mass of the sun would pull on you from a distance exactly like the sun does now. You could orbit it just as Earth orbits the sun, with no danger unless you drifted close enough to cross that invisible line. Still, the closer you get, the stranger things become. Time itself behaves differently near a black hole. If you hovered just outside the event horizon, your clock would tick more slowly compared to those far away. From your perspective, time would feel normal, but to the rest of the universe, you would appear to slow down, your movements stretching into an infinite pause. This time dilation is not just a curiosity, it's a profound consequence of how mass and energy warp space-time. In principle, you could use a black hole as a kind of time machine, traveling into the far future simply by spending time near its horizon. But it's a one-way trip. You can return to the outside universe only to find that centuries or millennia have passed in your absence. Even light behaves differently near a black hole. From a distance, the region around it appears warped, as if the stars themselves have been bent into a strange dance. This effect, called gravitational lensing, is one of the ways we detect black holes indirectly, by the way they bend and distort the light of background stars and galaxies. For many years, this was all we had. Indirect hints, like the invisible pull on orbiting stars or the X-ray flashes of matter falling inward. Now though, we are starting to see them, not directly, but in the glowing matter that swirls just outside the point of no return. And as we learn more, the image of the black hole as an inescapable destroyer is slowly being replaced by something subtler, a cosmic laboratory. A place where physics is pushed to its absolute limits. In fact, some scientists have speculated about using black holes, not just studying them from afar, but harnessing their power. A spinning black hole contains vast amounts of rotational energy. Theoretically, this energy could be extracted by clever means. For example, by sending in carefully aimed streams of matter and using the resulting interactions to siphon off energy. The Penrose process, named after physicist Roger Penrose, shows how this might work in principle. In more speculative visions, a black hole could power a civilization, serving as an engine with an efficiency far greater than any star. Feed it mass, and it radiates energy as the matter heats up in the accretion disk before crossing the horizon. Even a small black hole could outshine entire power grids for millions of years. There is also the idea of black holes as portals. Wormholes shortcuts through space-time are a staple of science fiction, and some solutions to Einstein's equations suggest they could be real, at least mathematically. In these scenarios, a black hole might be connected to a white hole, an object that expels matter instead of swallowing it. The two ends together could form a tunnel between distant parts of the universe, or even between universes. The problem is, as far as we know, such wormholes would be unstable. Any attempt to travel through one might cause it to collapse. To keep it open would require exotic matter with negative energy, something not known to exist in the amounts needed. Still, the possibility keeps the idea alive in theoretical physics, if not in practical engineering. But perhaps the most intriguing role for black holes lies in the deepest questions of cosmology and quantum theory. They may hold the key to uniting general relativity, our theory of gravity, with quantum mechanics, our theory of the very small. The conflict comes down to information. In quantum mechanics, information is never truly destroyed. The arrangement of particles, their states and interactions may change beyond recognition, but in principle, the information is preserved. Black holes, on the other hand, seem to destroy information. Throw a book into a fire, and its contents are gone in any useful sense. But the smoke and ash still contain the microscopic details from which, in theory, you could reconstruct what it was. Throw a book into a black hole, and that information seems to vanish from the universe entirely. Stephen Hawking famously argued that Hawking radiation carries no information about what fell in. If that's true, then the information is lost forever, a violation of quantum mechanics. This is the black hole information paradox, and it's one of the great unsolved problems of physics. Over the years, ideas have come and gone. Some suggest the information is somehow stored on the event horizon itself, encoded in a holographic way. Others propose that it leaks out in subtle correlations within the Hawking radiation. Still others wonder if black holes are not quite what we think, that the interior is replaced by some exotic quantum structure that preserves the information in ways we don't yet understand. Resolving this paradox may require a full theory of quantum. Gravity, a framework that unites the large-scale curvature of space-time with the quantum fluctuations of the microscopic world. And when we find it, it may transform not just our understanding of black holes, but of reality itself. The philosophical implications are hard to overstate. Black holes challenge our most basic notions of space, of time, of cause and effect, of what it means for something to exist. They are reminders that the universe is not built to be easily understood, that our everyday intuitions are local adaptations, not universal truths. In the vast timescales of cosmic history, black holes are both fleeting and enduring. Fleeting because they will one day vanish. Enduring because they will outlast almost everything else we know. From the collapse of massive stars to the evaporation of the last giants in a dark, empty universe, they form a thread through the entire life of the cosmos. They are birthplaces of questions and graves of certainty. And perhaps that is why they fascinate us so deeply. In them, we see both the ultimate limits of knowledge and the possibility of going beyond them. We may never cross an event horizon, but we can still stand at its edge, looking out or in, and imagine what lies beyond. Black holes are not simply the end. They are also a beginning of new physics, new ways of seeing, and new reasons to explore. The darkness at their center is not emptiness. It is the absence of everything we know, waiting for us to fill it with new understanding. Black holes are not all born equal. Some come from the predictable deaths of massive stars. Others may have been forged in the furnace of the very early universe. And some are so colossal that their origins remain one of the great mysteries of astrophysics. The simplest birth story is also the most violent. A massive star spends millions of years fusing lighter elements into heavier ones in its core. This fusion pushes outward, counteracting the inward pull of gravity. But once the core runs out of fuel, fusion stops. Gravity wins. The core collapses, and the outer layers are blasted away in a titanic supernova. If the star was massive enough, typically more than about 20 times the mass of the Sun, nothing can stop the collapse. The core shrinks past the point where even neutron degeneracy pressure, the force that props up neutron stars, can resist gravity. It falls inward until a singularity forms, a point of infinite density in classical theory, and an event horizon seals it off from the rest of the universe. This is the origin of a stellar mass black hole. They range from a few to perhaps a few dozen solar masses, though mergers can produce heavier ones. In our galaxy alone, there are probably millions of them. Invisible except for the rare cases where they feed on a companion star lighting up in X-rays. But black holes don't have to be stellar in size. At the other extreme are the supermassive black holes, with masses millions or billions of times that of the Sun. These giants lurk in the centers of galaxies, including our own Milky Way, whose central black hole, Sagittarius A*, weighs about 4 million suns. How such enormous objects form is an open question. One idea is that they grew from the collapse of the first massive stars. Billions of years ago, feeding on gas and merging with other black holes until they reached their current size. Another is that they formed directly from the collapse of vast clouds of primordial gas, bypassing the star stage entirely. Whatever their origin, they are central to the life of galaxies. The growth of a supermassive black hole and the evolution of its host galaxy appear to be linked. Feed the black hole enough gas, and it can unleash jets and winds so powerful that they blow gas out of the galaxy, shutting down star formation. This feedback may help explain why galaxies stop making stars after a certain point. Between the stellar and supermassive extremes lies an elusive middle ground. Intermediate mass black holes, hundreds or thousands of times the Sun's mass. They are hard to find, but recent gravitational wave detections from mergers have provided tantalizing evidence that they exist. They may be the missing link in black hole growth, the seeds from which supermassive giants sprout. Then there are the truly exotic possibilities. Some physicists have proposed the existence of primordial black holes, formed not from stars, but from density fluctuations in the hot, dense soup of the early universe. In the first fraction of a second after the Big Bang, regions just slightly denser than average could have collapsed directly into black holes, some tiny, some massive. If they exist, small primordial black holes might be evaporating right now in a final burst of Hawking radiation. Larger ones could still be around, quietly roaming intergalactic space, or even contributing to the mysterious dark matter that makes up most of the universe's mass. There is no confirmed detection yet, but the search is ongoing. Some surveys look for their gravitational lensing effects on background stars. Others listen for the fleeting chirps of their mergers in the fabric of spacetime. Finding them would not just confirm a new kind of black hole, but also give us a window into the conditions of the early universe. Once born, black holes can grow. They do this by feeding on gas, on dust, on stars, on other black holes. Gas falling into a black hole forms an accretion disk, spiraling inward and heating up to millions of degrees. This hot gas radiates intensely, often outshining the entire galaxy. When feeding is particularly extreme, the black hole becomes a quasar, a beacon visible across billions of light years. In the distant universe, we see quasars blazing at a time when the cosmos was less than 1 billion years old. Proof that supermassive black holes could grow rapidly under the right conditions. But black holes can also grow by merging. When two galaxies collide, their central black holes sink toward the center of the newly formed galaxy. Over millions of years, they spiral closer together, eventually merging in a cataclysm that sends ripples through spacetime. Gravitational waves. We have only recently begun detecting these waves, but they confirm a prediction of Einstein's theory and open a new way of studying black holes. Each detection tells us about the masses, spins, and distances of the merging black holes. And collectively, they are revealing the population and history of black holes across the universe. Growth, though, has its limits. A black hole can only feed so fast before the radiation from the infalling gas pushes back, limiting the rate at which more can fall in. This limit, called the Eddington limit, means that even the hungriest black holes can't grow infinitely fast, though they can come close under extreme conditions. Over time, though, even the mightiest black hole will stop feeding. The galaxy around it will grow old, its gas supply depleted. The black hole will settle into a long, dark existence, perhaps occasionally devouring the odd star that wanders too close. And then, over unimaginable spans of time, it will slowly evaporate. Hawking radiation, though feeble for large black holes, is relentless. Given enough time, far, far more than the current age of the universe, even a supermassive black hole will vanish in a final flash of energy. If the universe continues expanding forever, Black holes will be among the last luminous objects. Long after the stars have burned out, long after the galaxies have faded, they will remain. Solitary, ancient, slowly leaking away their mass until they are gone. In that far future, the universe will be cold and empty, filled only with thin radiation and the ghosts of what once was. And yet, even in their death, black holes will have shaped the cosmos. They will have governed the growth of galaxies, seeded new structures, and challenged our understanding of the deepest laws of nature. Black holes are not just astrophysical objects. They are stories of creation and destruction, of matter and energy, of the interplay between the known and the unknown. They are reminders that the universe is stranger than we can imagine, and yet real enough to study, to measure, and to understand piece by piece. And perhaps that is their greatest gift. They show us that the edge of knowledge is not an ending, but an invitation to look deeper, to think harder, and to embrace the mystery. Approaching a black hole is like walking toward the edge of the known universe. From a distance, it is invisible, a perfect void against the stars, revealing itself only by the way it warps the light of everything behind it. Stars bend into arcs. Background galaxies distort into smeared crescents. The night sky becomes a surreal canvas where space itself is painted on curves. As you drift closer, the gravitational pull becomes undeniable. Even without seeing the black hole directly, you can feel the space around you stretching. It is not a force you can push against, like wind or water. It is the geometry of the universe itself changing under your feet, or rather, beneath your ship. The first clear sign of the black hole itself is the accretion disk, if it is feeding. Matter falling inward forms a thin, bright ring around the event horizon, heated to millions of degrees by friction and compressed into brilliance by gravity. This disk blazes in X-rays and ultraviolet light, though your human eyes would see it as a blinding white-blue halo. If you approached from above the poles, you might see the jets. Narrow beams of plasma launched at nearly the speed of light, powered not by the black hole itself, but by the twisted magnetic fields in the swirling disk. These jets can stretch for thousands of light years, cutting through interstellar space like cosmic searchlights. As you come closer, time itself begins to change. Not for you, your clock still ticks normally, but for anyone watching from a safe distance, they would see your approach slowing, your ship appearing to hover just outside the event horizon, your last moments stretched into infinity. From their perspective, you never quite fall in. From your own perspective, though, there is no pause. You cross the event horizon without noticing any sudden boundary. There are no lights, no sounds, no alarms. It's just the continued pull inward. But the rules have changed. Outside, you could move in any direction. Inside, every path, even the one you think of as forward in time, leads inevitably toward the singularity. If the black hole is small, the tidal forces will become fatal long before you reach the singularity. Gravity is stronger at your feet than at your head, stretching you lengthwise and squeezing you sideways in a process sometimes called spaghettification. This is not a slow event. In a stellar mass black hole, it happens in milliseconds. But in a supermassive black hole, the story is different. Its event horizon is far larger, and the gradient of gravity across your body is gentler at the crossing. You could fall through without noticing much at first. You might have minutes, hours, or more before the tidal forces rise to lethal strength. What happens then depends on physics we do not yet fully understand. Classical general relativity predicts a singularity, a point where density becomes infinite and the laws of physics as we know them break down. But quantum mechanics refuses to accept true infinities. Somewhere between these two frameworks lies a description of what actually happens, but we don't have it yet. One idea is that the singularity may be replaced by a quantum core, a region where space and time themselves are quantized, where information about everything that fell in is somehow preserved. Another is that the singularity never forms because some new physical process halts the collapse at the smallest scales. And then there's the most speculative possibility, that black holes may be gateways. Not in the science fiction sense of a portal you can fly through and emerge somewhere else in the universe a second later, but in the sense that the inside of a black hole could be connected to another region of space-time entirely, perhaps even another universe. Mathematically, solutions to Einstein's equations allow for wormholes, shortcuts through space-time, and some versions link a black hole to a white hole on the other side, where matter is expelled instead of pulled in. In reality, these wormholes are unstable and would collapse instantly under the slightest disturbance, but they keep the door open to intriguing possibilities. There is also the mystery of information. In physics, information means the complete description of the state of a system, the exact arrangement of all its particles. Quantum mechanics says information cannot be destroyed. But when matter falls into a black hole, where does that information go? Hawking initially suggested it was lost forever, erased at the singularity. But this would violate quantum theory. Later, it was proposed that the information might be encoded in the Hawking radiation emitted as the black hole evaporates. This leads to the idea of the holographic principle, that the three-dimensional contents of a region of space can be fully described by information stored on its two-dimensional boundary. In a black hole, that boundary is the event horizon itself. If this is true, then everything that falls in might still exist in a scrambled, unrecognizable form, on the surface of the black hole, smeared across it like a cosmic storage device. These are not settled ideas. The black hole information paradox remains one of the deepest open problems in physics, a riddle at the meeting point of gravity, quantum mechanics, and thermodynamics. Its solution could be the key to uniting Einstein's theory with quantum theory, a goal physicists have pursued for nearly a century. Outside the event horizon, black holes still shape the universe in profound ways. Their gravity binds stars into tight orbits, as in the case of Sagittarius A* in the Milky Way's center. Their feeding can trigger or quench star formation, regulate galaxy growth, and seed vast cosmic structures. Even wandering black holes, drifting through interstellar space after being kicked out of their birthplaces, can sculpt the gas and stars they pass. Some may travel in complete darkness, never feeding enough to reveal themselves, invisible but no less real. There is also the strange possibility of binary black holes, two of them locked in orbit around each other. They spiral closer over millions of years, radiating energy in the form of gravitational waves, until they merge in a final burst of space-time ripples. Such events, detected by instruments like LIGO and Virgo, have already revealed black holes of unexpected masses and hinted at new ways they might form. Some may be remnants of massive stars in dense star clusters. Others could be products of earlier mergers, a cosmic cycle of black hole births and deaths playing out on grand timescales. If we think far into the future, to the era after the last stars have burned out, black holes will dominate the cosmic landscape. Stellar mass black holes will persist for quadrillions of years, slowly evaporating through Hawking radiation. Supermassive black holes will outlast even them, surviving for unimaginable spans, up to 10,100 years before finally fading away. When that happens, the universe will be dark. There will be no more galaxies, no more stars, no more light as we know it. Only the faint hiss of radiation from the last black holes as they vanish. It is a bleak vision, but also a reminder of the sheer scale of cosmic time. Everything we know, everything we see, happens in the blink of an eye compared to the lives of black holes. And yet, here we are, in the tiny sliver of time, when the universe is young enough to still sparkle with galaxies, and old enough for us to understand the monsters lurking among them. Black holes are both destroyers and creators. They tear apart stars, but also give birth to new understanding. They hide their interiors from us, but reveal the structure of space-time itself. They are puzzles made of gravity, and each piece we solve brings us closer to the full picture. If black holes are so perfectly dark, how do we even know they're there? The truth is, we almost never see a black hole directly. Instead, we notice the footprints they leave on the universe, the gravitational distortions in the orbits of nearby stars, the streams of hot gas spiraling toward an invisible center, the occasional outbursts of high-energy radiation when matter plunges inward and vanishes. One of the clearest examples is our own galaxy center, Sagittarius A*. The Milky Way's central supermassive black hole sits 26,000 light-years away. For decades, astronomers studied the orbits of stars around it, particularly one called S2. Every 16 years, S2 swings perilously close to the invisible mass, whipping around it at thousands of kilometers per second. Only something with a mass of 4 million suns, confined to a region no bigger than our solar system, could produce such a gravitational pull. In 2019, the Event Horizon Telescope, a network of radio observatories scattered across the globe, gave us the first direct image of a black hole's shadow. It was not a crisp photograph in the everyday sense, but a reconstruction from vast amounts of radio data, showing the glowing ring of matter around the supermassive black hole in galaxy M87. This image was a human milestone, proof that the predictions of general relativity hold true even at the edge of the abyss. And in 2022, the same technique gave us our first image of Sagittarius A* itself. Seeing the place at the heart of our galaxy, a region so distant that light takes tens of thousands of years to reach us, was more than just science. It was an emotional moment, a connection to the structure we live within, to the gravitational anchor that keeps the Milky Way together. But even without such images, we have other ways to track black holes. When two black holes collide, they send ripples through space-time, gravitational waves that race outward at the speed of light. Instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo can detect these ripples by measuring distortions thousands of times smaller than a proton across their laser arms. Since the first detection in 2015, we've recorded dozens of such events. Each one tells a story. Two massive stars that died as black holes, their orbits shrinking over millions of years, until they merge in a burst of energy greater than all the light. From all the stars in the observable universe, for a fraction of a second. These detections are not just confirmations that black holes exist, but let us measure their masses and spins, test general relativity under extreme conditions, and even hint at entirely new populations of black holes we didn't expect. Ones heavier than stellar collapse alone should produce. The idea that we might be surrounded by far more black holes than we thought is a tantalizing one. Some scientists have proposed that primordial black holes, tiny black holes formed in the chaotic, dense moments just after the Big Bang, could be scattered through the cosmos. If they exist, they might even account for part of the mysterious dark matter that shapes galaxies but does not emit light. Detecting them would be challenging. Small black holes would give off almost no radiation unless they happen to swallow something. We might find them through microlensing, the way their gravity bends light from background stars, or by spotting the brief flashes of their final evaporation through Hawking radiation. But whether we're talking about black holes born from collapsing stars, giants grown in galactic centers, or hypothetical primordial ones, they all share the same defining feature: the event horizon. That boundary is not a solid surface. If you fell in, you wouldn't bounce off. But it is a point of no return, a place where space and time are warped so completely that nothing can escape. What lies beyond remains hidden from us. Our telescopes, no matter how advanced, can only study the space outside. And yet, what happens inside shapes everything outside. The rate at which a black hole spins can determine how tightly its accretion disk coils, how powerful its jets become, how much it influences the surrounding galaxy. This is one of the reasons scientists are pushing for a new generation of observatories, ones that can see the universe in gravitational waves, X-rays, and radiolight all at once. Together, these instruments could give us multi-messenger astronomy, a way to watch black holes in several colors of physics, revealing more than any single technique could. In the near future, space-based gravitational wave detectors like LISA laser interferometer space antenna will be able to pick up the slow, deep frequency signals from supermassive black hole mergers, something ground-based detectors cannot do. Imagine listening to the universe as two titans, each millions or billions of times the sun's mass, spiral together over years, their gravitational song rising until they finally collide. X-ray telescopes, meanwhile, will continue to study the hot inner edges of accretion disks, where matter orbits at near light speed. Radio arrays will map the structure of jets across entire galaxies. Even neutrino observatories, detectors buried deep in ice or water, may one day trace high-energy particles back to black holes. The more we look, the more black holes turn out to be essential to the story of the cosmos. They are not rare. They are not exotic exceptions. They are woven into the fabric of galaxy evolution. Without them, the Milky Way might not have formed the way it did. Without them, the balance between star birth and star death might have been entirely different. There's a strange symmetry in this. Black holes are the most extreme outcome of gravity, regions where it overwhelms every other force. Yet their presence can regulate the very galaxies they inhabit, preventing runaway star formation that would burn through gas too quickly. In some sense, they are like the quiet governors of the universe, their unseen influence shaping the pace of cosmic growth. And yet, in another sense, they are reminders of how temporary everything is. Stars live for billions of years, but black holes can persist for numbers so large we cannot meaningfully grasp them. Still, even they are not immortal. When the last black hole evaporates, the universe will be a very different place. No stars will remain to light the night. No galaxies will swirl in the dark. Just a cold, empty expanse, perhaps filled with particles so diffuse that no two will meet in the remaining lifetime of the cosmos. In that far future, the memory of black holes will be gone, unless some other form of intelligence, somewhere, has found a way to archive the history of the universe. But for now, here in this brief age, when the cosmos is still rich and active, black holes are our teachers. They force us to confront the limits of our knowledge, to stretch our physics into domains it was never meant to handle, to imagine realms beyond our senses. They are mysteries we can never touch, and yet they are all around us, guiding the flow of matter and the fate of galaxies. They are the most silent of cosmic actors, but their stage is the entire universe,